Determine the force in members BC, CI, DI, and HI of the truss and state if the members are in tension or compression. To begin, first of all, we need to convert our distributed load into concentrated load. And using the principle of a one-way slab system, we know that our external concentrated loads will be 12 kilonewton each, and our internal concentrated loads will be 24 kilonewtons each. Once we have that, now we have to determine where we want to cut. And the best possible place to cut would be between C and D. Now let's draw the free body diagram of this cut. And we're going to use left hand side of this cut. Pardon me, the right hand side, because it's easier to solve. You can pick any side, it doesn't really matter because just extra work, but you'll get the same solution no matter which side you decide to solve with. And here we have our unknown friction force CD, and then we have another diagonal force TI, and one more unknown HI. Before we proceed, we need to determine our angles here. So angle theta and our angle beta. For angle theta, we know the distance between C and D, which is 2 meters, and we can find our distance or length of member CI later on, once we find our angle beta, which is also same angle for at angle at joint H for force HI. Our angle beta is 16.70 degrees. Now we can find the length of member CI. It's simply going to be tan of 16.7 degrees equals to CI divided by 6 meters, and our CI lengths come up to be 1.8 meters. Now we can use tan 2 over 1.8 1.8 over 2, pardon me, and we get our angle as 41.99 degrees. Now to solve, there are many ways we could solve this. I'm gonna take a moment about the point I. In this case, it will be our imaginary point. So we're going to have force CD, and we have already found our length of CI, and that's how far our D is. So it's 1.8 meters. And then we're going to have our clockwise external reaction forces. So we have 24 kilonewton. First one is 2 meters away, and second is 4 meters away. Then we have clockwise 12 kilonewton, 6 meters away, all equals to 0. So for CD, we get a solution as 120 kilonewton positive. So this means we assumed our vector direction to be correct. And this member CD is in tension. Now we can take movement about the point D. And this would help us find our solution for HI. We're gonna have clockwise 24 kilonewton, 2 meters away, and clockwise 12 kilonewton, 2 meters away. Then we have both horizontal and vertical components of HI. So in this case, it's gonna be horizontal component is in clockwise, and the vertical component doesn't matter because it's exactly right at D, therefore doesn't create any moment arm. And we get our solution for HI as 83.52 kilonewton, and the solution is in negative, therefore our vector is in wrong direction. Switching it over, we get a solution in positive, and also tells us that this member is in compression. Now that we have our HI, we can simply find our DI by either taking forces in X or Y direction. We're going to do it in X direction because it's a little bit easier because of lesser amount of forces to deal with. So we're going to have our force CD negative 120 kilonewton, to have positive horizontal component of HI, which is simply cos 60.70 times 83.52 kilonewton. And then we have positive cos 41.99 degrees times our unknown force DI, all equals to 0. Solving for force DI, we get our solution as 53.82 kilonewton. This means this angle or this member is in compression as well. Now we're left with to find our solution for member BC and CA. To solve this, we can use method of joints. So at joint C, we have external reaction force of 20 kilonewton, force CD, which is 120 kilonewton, and our unknown reaction pardon me, our unknown reaction, pardon me, our unknown force member PC, and then we have our unknown force CI. Sum the forces in X direction, and we solve for BC. We get our solution as positive 120 kilonewtons, and this member is in tension. And then we're going to sum the forces in Y direction and solve for CI, and it comes up to be 24 kilonewton, and this member is in compression.